Right, so here we have Griffiths quantum mechanics, problem 1.5. So he says, consider the wave function so this is the absolute value of x, and we have this phase like that. Alright, so, consider this wave function. A, lambda, and omega are all positive real constants, and the first thing we have to do is normalize it. So we're just going to find out what A is, basically. Alright, so part A, we're going to basically set this equal to 1. So we're going to find out what A is. Alright, so we have an A squared, which can come out front since it's a constant. We have an E to the minus 2 lambda, absolute value of x. And then when we do the complex conjugate and all of that, the phase will drop out. We'll have an e to the I omega t and an e to the minus I omega t, and those will drop out. So these phases don't matter at all once you actually take the square of, or the square of this wave function. They all go away. Alright, so this is going to be equal to 1. The way I'll handle this absolute value is I'm just going to basically reflect the whole problem across the y-axis and only go from 0 to positive infinity and multiply it by 2. So that's a 2a squared, 0 to positive infinity, and then just this same, and this will just be an x instead of the absolute value of x, since we're only going in the positive x range. Alright, okay, so this is equal to 2a squared, and then we have an e to the minus 2 lambda x divided by minus 2 lambda, evaluated from 0 to positive infinity. Okay. Right. So we're just going to, let's go ahead and divide out these 2's. We have a minus a squared over lambda, and then we get 0 minus 1, that, and all of this is set equal to 1. So this means that we have an a squared over lambda equals 1. So a squared equals lambda. So a equals the square root of lambda. So we have our wave function. Now we're just going to plug that in right up here to get our normalized wave function. Square root of lambda, e to the minus lambda, and then absolute value of x here, and then we have that phase factor. Like that. Alright, so here's our normalized wave function, and we're done with part A. So part B says determine the expectation values of x and x squared. Alright, well, the expectation value of x. I'm going to do that same, well, if we break the wave function into two halves from minus infinity to 0 and 0 to infinity and do our integration that way, that helps with the absolute value on the x. Alright, so let's see. We've got, if we do okay, so we're multiplying by x on the inside here, and then we have this square root of lambda squared for each of these integrals. So we can bring that out to the front. Phase factors drop out again, and so for negative, we're going to go ahead and make this positive e to the positive 2 lambda x. So basically, that's how we're handling the absolute value. We'll just throw another, as in this domain here, from negative infinity to 0. We'll go ahead and add another sign change up to the top to keep our absolute value. Alright. And now we'll go from 0 to infinity, x, and then here we just have our normal okay. So I did this a little bit differently than I did before. Essentially this integral is going to give us 0. Alright, well, to save on time in the video, we'll just look at it sort of graphically. So basically we just have an even function multiplied by an odd function. So if we were to sort of sketch this out a little bit, the e to the minus lambda absolute value of x part, that's going to, because of the absolute value of x, we'll get the same, it'll be an even function, it'll be the same across this y-axis here, so it'll be something like this decaying exponential on both sides. And if you just draw the x that we're taking this expectation value of, that's going to be negative for negative x and positive for positive x. It'll be an odd function, which just kind of comes up through the middle. All right, now when we multiply them together, this side will be multiplied by a negative number, this side will be multiplied by a positive number, and basically we'll just get this side flipped over like that, and the other side, and these will go to finite value of lambda and minus lambda, so they're not just like shooting off to infinity here, at least in this direction. Alright, so basically when we take the integral across from minus infinity to plus infinity, we have exactly the same amount of area below the x-axis as we do above the x-axis. So anyway, that's a more graphical way of showing why this is 0 and without going and doing the whole integration. Alright, so hopefully that turned out faster. whether or not it's faster in your head than it is doing out the integrals, at least for me. All right, but unfortunately, we have no such luck when we find the expectation value of x squared, because then we have this even function for this exponential part, but then the x squared is this parabola, which is also even. So no luck there. All right, so basically, if we we'll just take this one in two parts as well. Whether or not we have to do this, yeah, I don't know. But yeah, because it's symmetric, what the heck, I'm just gonna split it into two parts. They'll both be the same, so anyway, I'd rather integrate from 0 to infinity rather than minus infinity to infinity, so I'll do it the other way too, I'm sure. All right, so here's what we're looking at now, and you can do this with the integration by parts. You get the same answer, but you have to do it twice. It's going to take a little bit of time, but if you look up here, Gaussian integrals, there's a nifty little trick with like differentiating underneath the integral, kind of like a Feynman trick, I don't know, but you can get a nice little formula for this type of integral in general. So here's a nice reason why we want to integrate from 0 to infinity rather than both. It matches up real nice with this formula. And I can never ever remember this formula on tests. So I need to just learn the whole derivation thing. All right, so in our case, if we just look at this integral, we have an n equals 2. Alpha equals 2 lambda. And that's all we need. So our expectation value of x squared is equal to 2 lambda. This part now for the integral, we just have a 2 factorial on the top, which is just 2. And underneath we have 2 lambda to 2 plus 1, so 3. All right, so up top we have a 4, anyway, we have 2 powers of 2 on top, 3 on the bottom, so we end up with 1 power of 2 on the bottom. We have 1 power of lambda on top, 3 on the bottom, so we end up with 2 on the bottom. And I hope I did that right. I think I did. Okay. All right. So there we go. All right. This is correct. Yes. Okay. Check my notes. All right. So now on to part C. So he says find the standard deviation of x and sketch the graph of psi squared as a function of x and mark the points to illustrate the sense in which sigma represents the spread in x, and what is the probability that the particle would be found outside this range. All right, well, standard deviation of x, just call it the variance here. We have our little buddy like that. All right, now this part we know is 0, so we can just forget about that for now. And then we know this part is just 1/2 lambda squared. So this gives us the standard deviation of, we just take the square root. Bring lambda out front and then square root of 2, like that. Alright. So if we look at the side squared, where did I put it? There we go. Alright, so we just get square of this square root of lambda, so that's just 1 power of lambda here. And then we have an e to the -2 lambda absolute value of x. And then the phase factor goes away again. Alright, so just draw a quick sketch. Alright, well, when x is equal to 0, this e goes to, this exponent here all goes to 1, and we have 1 times lambda. You know, maybe there's some way of finding some other points along here, but we do know it's going to drop off just exponentially in each direction. It'll be mirrored across the y-axis here. I guess you could, I've been calling it the y-axis, but the psi squared axis, whatever. Alright, so if we plug in our standard deviation, maybe that will tell us something. So we put that in for x. Well, our lambda will cancel out, and we're just left with, so let's see if I can write this out. I'll just call it as x equals sigma here. So we have lambda e to the -square root of 2. Alright, so this should let us get some kind of point. You could plug this into a calculator and find out what decimal value this has here. But you'll find, I'm going to be a little sloppy, you can just find there's some value right through here where you get this this number right here, whatever, call it just psi sigma squared, right? That's what it's already called. Whatever, that's what it's already called. Just write that in. Something like that. Alright, so you can find that on a calculator, and it'll just, and then find this decimal. It'll be some fraction of 1, and then you just go up. Here's 1 at lambda. Here's that value. Boom, boom. You find these two positions, and here's sigma and a minus sigma where it comes down and hits the x-axis. Alright, so that gives an idea of the spread. It could be better if we actually plugged it into a calculator and plotted this in much more detail. Alright, so we've sort of illustrated the sense in which sigma represents the spread in x. What is the probability that the particle would be found outside this range? So, as usual, to answer that question, we're going to find the probability that it would be found inside that range, and then we'll just take 1 minus that probability to find what it is outside. Alright, so we're centered around 0 this time, so we don't have this average thing to worry about. We just go from minus the sigma to plus sigma. Okay. All right. Again, we'll have lambda out front, which is square root of lambda squared, and our phase factor again gets thrown out. So we have an e to the minus 2 lambda absolute value of x again. All right. So gonna do the same thing since it's an even function. I just don't like those absolute value signs, so we'll just multiply it by 2, take only the positive half of everything, and we'll just use this to get rid of that absolute value sign. Alright, just like so. So e to the minus 2 lambda x minus 2 lambda on the bottom, so put the minus sign up front, and then 2 lambda on the bottom, and check that out. That cancels out nicely. And this is from 0 to sigma. So we can just flip these, the sigma on the bottom and the 0 on the top, and get rid of that minus sign too. Alright, well, e to the 0 is 1 minus this e to the minus 2 lambda sigma. Okay, now the probability of being on the outside, which is our original question, is just 1 minus the probability of it being on the inside. So we end up the 1 minus 1, 0 minus this is just plus this e to the minus 2 lambda, and then let's go ahead and plug in our sigma. Our sigma was 1 over lambda times the square root of 2. Alright. So the lambdas cancel out, and we just have e to the minus, and then we can take the square root of 2, divide out here from the bottom to the top. So here's what we're finally left with. This is the probability that, don't even remember what we're talking about anymore. So just a particle, right? It's what is the probability that the particle would be found outside this range? Alright, and there it is. E to the minus the square root of 2 is the probability the particle is outside of, or is further than 1 standard deviation from the